A breakthrough AI video editor from Google is set to transform content creation forever. Google has released a new AI model called Dreamix that has the ability to generate videos by utilizing image, video, and text inputs. The Dreamix video editor maintains realism by providing an output that is consistent in color, posture, object size, and camera pose. The AI system uses video diffusion models and a text prompt to edit the input. This approach involves reducing the input video, adding artificial noise, and processing it to generate a new output that retains some of the original video's properties and re-renders others according to the text input. Although Dreamix is currently unable to generate videos from just a prompt, it can, however, modify existing materials using text prompts. Video diffusion models have thus far only been successfully applied to image AIs like DALL-E 2 or the open-source Stable Diffusion, but this approach also holds great promise for the future of video editing. The way it works is that the Dreamix artificial intelligence employs a video diffusion model to merge low-resolution spatiotemporal data from the source video with high-resolution synthesized information aligning with the text prompt during the inference stage. The reason behind this approach, as stated by Google, is that retaining some high-resolution information from the original video is necessary for achieving high-fidelity output. To address this, the model goes through a preliminary stage of fine-tuning on the source video, which significantly enhances the fidelity of the final output. To overcome a limited extent of motion change, the researchers incorporate a mixed objective, which includes the original objective along with fine-tuning on the unordered set of frames. The latter is achieved through the use of masked temporal attention, which prevents the fine-tuning of temporal attention and convolution. This approach enables Google to introduce motion into a static video. Meanwhile, another incredible technological leap forward in AI-driven video editing just happened, as Runway recently unleashed their own game-changing Gen 1 video editing model, which also allows anyone to visually transform videos using text prompts, but this one's different. Gen 1 breathes new life into existing videos, and by incorporating your own images, this model can be enhanced to produce better transformations. Furthermore, Gen 1 makes it possible to create entirely new footage without filming anything at all, like making a cityscape of towering skyscrapers from a handful of loosely organized notebooks coupled with some text commands. The Gen 1 model can also identify and manipulate specific objects in a video. For example, transforming a golden retriever into a Dalmatian or adding texture to untextured 3D objects with simple text prompts. Here's how it works. The extension of latent diffusion models to video production has been made possible by adding temporal layers to an already trained image model and training on pictures and videos. This has resulted in a model that adjusts films based on sample text or pictures, with a complete editing procedure done at the inference time without further per-video training or pre-processing. The team has demonstrated their complete mastery of consistency in terms of time, substance, and structure, as well as the possibility of controlling temporal consistency at inference time by concurrently training on image and video data. They also conducted user research, showing that their technique is preferable over several alternative approaches. Furthermore, by focusing on a small group of photos, they were able to modify the trained model to produce more accurate movies of a particular subject. But hold on to your seat, because in yet another amazing advance in AI-powered video editing, researchers from the University of Maryland have introduced a text-driven video editing approach that takes shape distortion into account, known as shape-aware text-driven layered video editing. To tackle this challenge, the researchers first propagate the deformation field between the input and edited keyframe for the entirety of frames. They then employ a pre-trained text-conditioned diffusion model as a reference to enhance the accuracy of shape distortion and fill in unseen regions. The experimental results of the approach demonstrate that it can accomplish shape-aware, consistent video editing and perform favorably when compared to current state-of-the-art methods. The approach is founded on a pre-trained NLA that divides the video into cohesive collections of maps with their associated per-frame UV mapping. The dense semantic correspondence between the input and edited keyframe behaves as the link between the input and output videos for per-frame deformation via the UV mapping and atlas. The deformation module then maps the edits back to the atlas through the original UV map, utilizing the semantic correspondence of the keyframe. The deformation vectors at each pixel are transformed into the atlas space with the same UV mapping field. Consequently, the UV map samples the color and deformation vectors onto each frame to deform the original UV map, while preserving the edited shape. Additionally, the deformation maps are linearly interpolated to easily insert the object shape without necessitating additional frame interpolation methods. In another advance, AI is also pushing the boundaries of object pose estimation with a brand new method called One Pose Plus Plus. Object pose estimation plays a vital role in various fields, such as augmented reality, robotics, and autonomous driving for identifying the position and orientation of objects within an image or video. And the objective is to generate a comprehensive representation of objects in the scene, encompassing their location, orientation, shape, size, and texture. One Pose is designed to streamline the process of object pose estimation for augmented reality purposes. Unlike traditional methods, it does not necessitate the use of CAD models or category-specific training. All that is required is a video sequence with annotated object poses. One Pose employs a feature matching technique that builds sparse object point clouds, links 2D and 3D key points, and calculates the object's pose. However, this approach faces challenges with objects that lack texture, as complete point clouds are hard to reconstruct using key point-based structure from motion, resulting in failed pose estimations. One Pose Plus Plus is a new approach that builds on One Pose to address the issue of low-textured objects. It uses a key point-free feature matching method to obtain the correct semi-dense object point cloud from reference photos. The method then computes the object pose for test images in a progressive manner by linking 2D and 3D correspondences in a step-by-step fashion. The method of using detector-free local feature mapping with transformers has been modified to be used for feature matching. This key point-free semi-dense technique is effective in pairing images and identifying correspondences in areas with low texture. It utilizes the centers of a grid in the left image as key points and locates sub-pixel accurate matches in the right image through a coarse-to-fine process. But the reliance of detector-free local feature mapping with transformers on two views can result in inconsistent key points and incomplete feature tracks, making the key point-free feature matching method unsuitable for use in One Pose for object pose estimation. To benefit from both methods, a new system was created to modify the key point-free matching technique for single-shot object pose estimation. The authors present a sparse-to-dense 2D-3D matching network that effectively creates accurate 2D-3D correspondences for pose estimation, utilizing the key point-free design. The coarse-to-fine structure of detector-free local feature mapping with transformers has been disassembled and integrated into the reconstruction pipeline to better adapt it for SFM. Moreover, self and cross-attention are employed to handle the long-range dependencies necessary for robust 2D to 3D matching and pose estimation of complex real-world objects, which often have repetitive patterns or low-textured areas.